Hey guys, Pankaj here. Welcome back. So in today's statistics video, I'm going to talk about central limit theorem, that is CLT. Okay, it is one of the most powerful and most famous theory in statistics or in mathematics, I would say. Okay, so let's see what I have. I'll share my screen. Okay, so let me read this. What is this, and what kind of fundamental concepts are there behind central limit theory? Okay, so central limit theorem (CLT) is a statistical concept that states the sample mean distribution of a random variable will assume a near normal or normal distribution if the sample size is large enough. Okay, so it may sound very confusing, but I'm going to prove it with the help of Python as well as in whiteboard. I'll explain this. Okay, so what basically it is telling, let's say you have very large population, right? And in previous video or a couple of previous video I talked about, right? Let's say you are going to collect height of all the male in the India or all over the world, right? It is practically impossible to do that kind of data collection, right? So what they do the sample collection. They will pick few people, maybe some thousand or 10,000 people, and from that sample they will be calculating a couple of statistical parameter, that is, let's say, mean and variance, right? And a lot of samples will be collected like that. And if you do a lot of data collection and very large samples are there, and if you take the mean of those large sample, that mean is going to tell, it is going to be, or they can tell like, okay, whatever mean I'm getting from all sample means, it is going to be exactly same as population mean. Okay, so basically you are trying to estimate the population mean by collecting so many samples of same size. Okay, that's what this particular line is telling. The central limit theorem CLT states that the distribution of a sample means approximates a normal distribution. Okay, so when you collect a lot of samples of same size, then the distribution of sample mean will be approximating or giving the estimate of normal distribution of population. Okay, that's what it is mentioned. Sample size equal to or greater than 30 are often considered as sufficient for the CLT to hold. So what exactly it means is, basically they are giving or they are telling like it is a thumb rule that you need to collect the samples more than or equal to 30 numbers. Okay, so your sample size should be equal to or greater than 30. Then only first two lines will be holding true. Okay, a key aspect of CLT is that average of the sample means and standard deviation will equal the population mean and standard deviation. That is what I told in the first line. A sufficiently large sample size can predict the characteristics of a population more accurately. So as the sample size is growing, it is give proper or like exact accuracy, or you can say like it will give the exact accurate estimate about the population mean and variance. Okay, that's what it tells. Okay, so let me go to the whiteboard and show this. Okay, so what they're telling, let's say you have data X, maybe it is population, which is following normal Gaussian distribution. So it has mu and sigma, that is nothing but a standard, variance. Okay, so as I mentioned, let's say N is very large, like 1 CR people. Okay, to do data collection for 1 CR people, it is going to be a little impossible, or practically it is not possible, right? So what they do sample collection. So out of this 1 CR, they will be doing the sample collection of, let's say, maybe 100 samples. Okay, and this sample will be from X1 to, let's say, X100. Okay, now they'll be doing another sample collection, which will be like again X1 to X100. And there will be another sample, let's say X3 equal to X1 till X100, and so on. If you do n sample collection, Xi equal to X100, then if you calculate the mean of this, right, X1 mean or X2 mean or X3 mean and so on equal to Xn mean, and if you take this mean of all the means, right, so let's say X1, X2, X3 plus Xn, and divide by total number of sample collected. Let's say you have collected total n sample, right? So whatever mean you are going to get, right? Let's say this mean is represented as this is going to be almost or exactly or maybe very, very much equal to the population mean. Okay, this is your population mean. And this is your sample mean. That is what central limit theorem, CLT, is telling. So let me reiterate once again. Let's say you have very large population and you are not able to calculate, like you are not able to do data collection exactly, right? You pick random sample, and that sample size you select, let's say your size of sample is equal to 100. You have decided the size. Okay, and do so many data collection or so many sample collection, but each sample size should be, let's say 100, because you have decided 100. Okay, and when you calculate the mean of each sample and you take the mean of all the means, all the sample means, right? So the whatever mean you are going to get, right, sample mean, that is going to be exactly or almost same as population mean. So now you know what is happening here, right? Let's say you don't know population mean, you collect all the samples, collect all the means of sample, and take the mean of all sample mean, right? Then you are going to estimate population mean without doing much calculation for the population sample. And that is the beauty of this particular theorem. Okay, and this is about mean. So S mean almost equal to population mean, right? What about variance? So variance of sample mean will be equal to close to sigma square. Okay, so this is your population mean, and this is nothing but your, sorry, not mean, population variance. Okay, and this is your sample variance. This is what your central limit theorem tells. So let's say you have all the sample collected, which represented as S. It is going to follow Gaussian normal distribution, where mean will be your mu, like sample, sorry, population mean, and variance will be equal to sigma square n, and this n being the sample size. So please remember these two formula. Okay, your sample mean is going to be exactly population mean, as n our sample size tends towards infinity. Basically your sample size is growing, then as it is going towards infinity, then your sample mean will be very much close to the population mean. Okay, and sample variance will be close to sigma square by, and this sigma square is nothing but your, it is coming from this particular population variance. Okay, so sample variance will be sigma square by n, and population variance is sigma square. That is what this theory tells. So let me go ahead and prove this by Python coding. So as usual, I'll be importing NumPy, NP, Pandas, Matplotlib, and C1, right? So let's go ahead and import it. Now I'm going to create some sample here. NP dot random dot randint. Let's say I'm collecting height of all the meal, right? So let's say starting with 120 and ending with 180, and I have, let's say, maybe thousand samples I have. Okay, this is basically normal population I'm talking. Okay, and the mean of this population is, let's say, print a dot mean. Assume that this is small data, though it is a small data, but this is a population. Population mean is a dot mean, and population variance equal to a dot var. Okay, this is what we got, 140 and 306. Okay, now let's go ahead and do the sample collection. So what I'll do, since I'm going to collect n number of samples, right? So what I'll do, I'll just write a for loop for I in range. Let's say I'm collecting all the samples 50 times. Okay, so 1 to, let's say, 51. So that exactly 50 times I'll get. And here I'm going to define sample size equal to, let's say, first I'll take 20 sample. So I'll show what is the difference. So as per theory, it is telling, right, here it is mentioned, your sample size should be greater than or equal to 30. Let's collect with 20 and see the variance. Okay, here, and I'm going to create temp variable np dot random dot choice, and from this choice I'm going to take the sample from A, and what is the size equal to, let's say sample size is nothing but sample size. Okay, what else? We have replaced 2, let it replace because it will be having unique values. Okay, now go ahead and print the, so sample 1 and its mean is this and variance is this dot format. So what is the sample number? That is I. So the first sample, and its mean is temp dot mean. Okay, and its variance is temp dot var. Okay, let's go ahead and print. So you see here, first sample is 149, 156. So we collected all the samples, and mean of each sample is there, and mean of variance is also there. Sorry, variance of each sample is also there. Okay, so instead of printing, what I will do, I'm just going to visualize the data. Okay, so what I'll do, I'll just create sample mean equal to this, sample variance equal to this. Okay, and I'm going to append it. First, I'll comment this part. So let's say m dot append. So what is that? First main temp dot mean, and variance will be variance dot temp dot var. Okay, and now let's go ahead and print it. Oh, sorry, plot it. So what we are going to do, we are going to plot each data, KD plot of each sample. Okay, so that KD will clearly tell what is your mean, what is your variance by looking into the data. I think for this, I can just print it here. So what I'll do, I'll just create 50 plots, plt dot subplot. So 1 to 50, right? Because we are going to have 50 data sample, and this will be your first number, sns dot kd plot, and here I'm going to plot temp. Okay, plt dot axis of plt dot. So let's see if it is printing. I forgot to change the number. The number I plt dot subplot 150 kd plot plt dot axis of. Okay, I got to know what is the problem. So plt dot subplot 150, this will be number. Oh, this is a mistake I did. So I want to have 50, right? So I'll just use maybe 10 rows and 5 columns. So why it is not incrementing? plt dot, yeah, plt dot figure fixed size, let's say give 10 by 10 so that we can clearly see all the figures. Okay, so here sample size increasing and why it is okay. This is another problem. X is off. For each plot, I don't want to give access. So what I'll do, I'll just add some labels here. So PLT dot title. So let's say title is first is your sample size equal to this and mean equal to this, and variance part we can remove right now. So I'm just going to list what is the sample size here. So sample size is 20, right? So what I will do, instead of taking 20, I'll start with 10 and keep incrementing it. Okay. So here sample size will be your sample size. Then mean will be your temp dot mean. And later let's increment sample size plus equal to maybe every 5 times. Okay. Yeah, let's do that. I think this should be fine. Okay, let me round it to one place. Okay, looks better. I want to increase the width of this. This is much better. Okay, so if you see here, if you notice, then population mean is 149, right? And here what is happening? See, the moment sample size start increasing, let's say here we are 10, 15, 20, 15. The moment you see more than 30 or 35, right, you'll see it is trying to hit the mean exactly same as population. Okay, you may see other also there 51, 50, 149, but a lot of variations will be there. But as sample size is growing, it is going towards infinity, right? It will be very much close to the population mean. That's what I wanted to show this with the help of graph by varying the sample size. Okay, and taking their mean. Okay, so once you got this particular mean, right, so I can prove it by taking the mean of each sample. So let's say whatever I got finally, this was the mean, right? So I will just take sum of m, and my sample, total sample I collected was how many? It was 50, right? So just divide by 50. So this will also prove you that my overall mean is nothing but very much close to the population mean. You see here, your population mean was 149.019, and this is nothing but the mean of all samples. That is 149.22. This is what is shown here, 149.22. Okay, and their variance will be how much? So we have what is the variance here? You can take variance also and divide by n, correct? So let me take a variance last value and divide by, let's say, 50. Did I not add here? I think I commented it, right? Now it should be fine. 5.91, correct? Yeah, so your population variance is 306 and it is coming here. This is your mean sample mean of, variance of the last value which we got, right? If you take the average and just do sigma square by n, then you are going to get almost very close to the close value of population variance. Okay, guys, so that's what central limit theory tells that. So let me remind once again, central limit theory will be used only when you have very large set of data, and with the help of sample size, where sample size will be greater than or equal to 30, you can easily estimate what is your population mean and population variance. Okay, so that's all about central limit theory. I hope you liked it. If you didn't understand, then please put your comment in the comment box, and I'll help you to reply. And you can easily understand. And I can probably put in the next video also, like what is the reason you did not understand, and probably you can easily get it later by, maybe I'll take another example also to solve your query. Okay, guys. So that's all from my side. Thank you so much. See you in the next video. Bye bye.